You're the bouncer.
You should be. Okay, so welcome to the last session of the workshop. Prizes for stamina. And which one's good? Oh, no, Snyder should give a talk on Trivalent.
Thanks for the introduction, and thanks for the organizers for the invitation. Yeah, so it's trivalent categories, trivalent tensor categories. The tensor is silent. And this is all joint work with Scott Morrison and Emily Peters. So I want to start by sort of motivating why I'm doing this with my life goal to find new tensor categories. I understand this is not everyone's life goal, and this is not what I do all the time, but it is sort of just a driving thing, like, you know, it's like Indiana Jones. You're just out there. You just want to find. Anyway, so that's my motivation here. I just want to find new tensor categories. I don't really care what they are. I just want to know if they're out there. So that's kind of my motivation. Now you might ask, why is this in an operators algebras? Operator algebras conference. And of course, the reason is there's a relation to bimodules over factors that is, of course, quite important. I should say very little I'm going to do has any analytic content. This is sort of like there's group theory and there's analytic group theory, right? And they're both great, and there's great analytic questions you can ask about groups, but you need to know some groups first. And I think it's sort of the same thing here. There's lots of great analytic questions you could ask about quantum groups and tensor categories that I'm not going to be asking, but you know, you want some examples to ask them about. So that I think there's kind of an interplay between the algebraic half of it and the analytic half, just like you need group theory to do analytic group theory. What's the status of trying to find new tensor categories? We want to know, are they new? Are they exciting? Are they different? So here's sort of the status of tensor categories that we know. All known examples come from, and this come from does a lot of work, quantum groups, by which I mean not some abstract notion of quantum groups, but the actual things that come from deforming classical Lie groups in some way. Okay, so quantum groups and Izumi quadratic categories. So you saw a bunch of these in Pinhas's talk. So they have one orbit of invertible objects and then another orbit of non-invertible objects. And that second, so the invertibles form a group. The non-invertibles should form a single orbit for that group. It might be rather large, like what happens in those 3 to the G graphs he was drawing, where you have a group out at the end of the spike and then another copy of the group on the inside. But there are also sometimes where the orbit is smaller than the whole group, and there are a bunch of examples like this. And everything comes from these two things, except one example, this thing that's called extended algebra. So there are these various exotic examples. Hagrup definitely fits into this. As Pinhas mentioned in his talk, we showed that a Seda Hagrup, once you take a more elaborate viewpoint of what comes from, also fits into this. But extended Hagrup, the third one, is still sort of out there. Now I should say a warning about this come from. Previous times I've given this thing, I've written 3 things on here, finite groups as well. But then I realized, like, when I say come from a quantum group, I'm including like doing all sorts of like groupy constructions. So I might as well say all the things coming from finite groups just come from the trivial category of vector spaces by applying these come from constructions. So when I say come from includes all of group theory. It includes free products, includes Morita equivalents. So let me say a little of that. So come from includes groups, free products, Morita equivalents, which you saw a lot of in Pinhas's talk, et cetera, et cetera, et cetera. And this is not, the come from isn't well defined, so there's no even precise conjecture here, but you kind of, you know, if you come up with something new, then everyone goes and tries to see if it comes from something they already know, and if they find it, you say it does come from, and if it didn't, you know, you wait 10 years, and then maybe someone else will. But great, okay, so this is what I'd like to get some feeling for whether this is really all that's out there or not. If you gave this talk, you know, in like the early 90s, you wouldn't have had, you know, before Izumi's work, you wouldn't have had that second family on there, and maybe we're missing some other things that are just as interesting. Okay, so how does one go about finding these things? What's the technique to find new things? Well, prove classification theorems. As proof of concept, this is where all weird exceptional things have always come from, like G2 or E8 or the monster. People didn't sit around, you know, in abstract thought and suddenly E8 came to them. They tried to classify what all the Lie algebras were and then ran across, oh, there might be this E8 thing, and then it really is there. So this is, as far as I can tell, I mean, the other thing is luck. You can be studying some totally different problem and then notice you've come up across something, right? But anyway, this is sort of the best way I know to look for things. From this point of view, it doesn't really matter. It's less important what classification you're trying to prove. Like, you can set yourself whatever parameters you want to see what everything is in there, and then you've done some kind of test of this. So the analogy I like is like you have some telescope and you point it at some part of the sky and you just see what you see, and then that tells you something about whether you know what all kinds of stars are, and then maybe you point it somewhere else, or maybe you use a different kind of telescope and you find out more things, okay? So the main types of classification theorems are small index, small rank. So Julia mentioned this morning, that this is one of the big things that the modular tensor category people are doing. So you could also put whatever adjectives you want here. So you could say, let's look for modular tensor categories with small rank. But the one I want to talk today is something called simple skein theory. But of course, there may be others, and it's interesting to think about whether there's better kinds of measurements than what we've been using here. So what do I mean by simple skein theory? So this is sort of not theoretically inspired. So the basic idea is I have some tensor categories, so there's a bunch of simple objects that I can tensor together and a bunch of maps between them. So I pick some favorite objects, or maybe just one favorite object. So I fix a favorite object. And some favorite morphisms of a specific sort. And so what am I saying? I have my favorite object. Say, you know, I was looking at like representations of GLV, and my favorite object was V. And now I start looking at tensor powers of V and all maps between them, but I only look at the ones that I can build out of crossings. This is like the Schur-Weil duality way of thinking about it. Then you can draw pictures for what kinds of maps you can build out of those. And then I want to say what kind of relations are there between those pictures, and I want to measure how complicated my category is in terms of those pictures that I'm looking at. So, so I realized just as I was about to start giving this talk that almost no one has talked about pictures for tensor categories. And so I need to probably, I'm going to write something, but then I probably need to impromptu add something here. So I want to say, and then we bound the growth of the n-box spaces for small n. So maybe I'm trying to think which example I should use. Maybe as an example, I'll use the thing I'm actually talking about in this talk, even though I'm going to give some other examples first. So the example I actually have in mind in this talk is something like you have a favorite object x, and then you have a favorite map that goes from x tensor x to x. And then what you can do is look at pictures that look like this. And this picture is supposed to represent, so what you do is you start at the bottom and you put an x for every copy of this strand. Okay, so at the bottom that's x tensor x tensor x. At the top I only have 3 x's. Let me give myself a little bit more space at the top. So at the top I have an x tensor x tensor x. So the whole thing is supposed to represent some map from x to the 4th to x to the cubed. Now what map is it? Well, every time I see a trivalent vertex, I interpret it using this map. Okay, so here that's easy. This just says take the middle 2 arguments and apply mu to get them down to 1. And here it then says take that argument and this one and get it down to 1. This gives a well-defined morphism. This one's a little bit trickier, but you interpret it as sort of rotation. So I could draw it, if I drew it like this, it would maybe be more clear. So as I go up, the first thing that happens is something appears, and that uses duality. So I should have said, oh, x I want to be self-dual. So an x be self-dual, and I want to map like this. So because x is self-dual, I can appear an x and an x dual from nothing. That's part of what it means to have a dual. And then I multiply these 2 things, and then I go there. So that's how I interpret trivalent vertexes that are sort of rotated around. Okay, so this is the kind of pictures we're allowed to do. And when I say the first few box spaces should be small, I mean look at the space spanned by diagrams with n boundary points. It doesn't really matter whether you put the boundary points at the top or at the bottom, because things are self-dual. That allows you to move them back and forth. So you just look at the space of maps spanned by these. As I add more pictures, of course I could draw infinitely many pictures like this. But if x is some nice small bimodule, you would only expect so many homs between these things, and eventually my pictures will only span some small space. And I want to say those numbers are small, and that's what it means for my skein theory to be simple, is that those numbers are small. Does that make sense? People understand what it means to do a simple skein theoretic classification? So I'm going to fix some kind of object, some kinds of morphisms, and then I want to understand all tensor categories that have such an object and such morphisms, and also have the property that these small Hom spaces, these invariant spaces of the first few tensor powers of x, are small. Okay? Great. So we are not the first people to do such a thing. So I'm going to talk very briefly, in very little detail, about some previous ones. So one of the big programs in this direction started by Bish and Jones, and then sort of taken over by Liu recently. So here you're looking at unitary. So this just means like they're, some of these things I'm going to say are more algebraic, and some include that you want some kind of star structure and some Hilbert spaces. Everything's still finite dimensional, but shaded planar algebras. So shaded here means you checkerboard shade the regions in your picture, so not the strands themselves, but the regions between the strands. Of course, you can't do that in the trivalent thing because 3 is not a multiple of 2, but you look at shaded pictures, and the shaded corresponds to subfactors because you have n inside m, and one of the shadings is n and the other one is m, and your lines are nm bimodules instead of nn bimodules. So you have shaded planar algebras generated by and here there's a weird convention. Because things are shaded, you have to have an even number of boundary points. So people usually divide the number of boundary points by 2. So I'll call that a shaded 2 box. So that means in the shaded world, that means it has 4 boundary points. So the shaded 2 box with the growth of these invariant spaces bounded by 1, 1, 3, 14. And they have a partial result for 1, 1, 3, 15. Okay, so what this means is the number of things with 0 boundary points is 1. That's basically always true. That's like the fact that you're looking at subfactors instead of sub-von Neumann algebras. And then this is that the number of maps from x to x is one-dimensional, and that's some kind of irreducibility. This is now the maps from sort of x squared to x squared. And then you want a 14 there, you want a 15 there. And there are a bunch of interesting examples. There's the Bish-Jones free products of temporally leads. There's the BMW. And then there's another example that's sort of a quotient of a quantum subgroup. Anyway, there's some interesting examples there. These definitely come from quantum groups in an appropriate sense. And once you allow free products, this comes from a free product of 2 different quantum groups. Yeah?
Clarify, why did you stop at the 4th entry? I mean,
yeah, so I'm implicitly sort of, in general, yeah, so it's because that's all you need. So as I'm doing this, you sort of, the nature of the game is at some point when you increase that number too high, it gets way too hard.
the 4th number? Or?
Well, for each number, like I could also try changing this 3 to a 4, and it would also be too hard. Okay? So you go until it gets too hard. Maybe when it gets too hard, you can still make some progress by increasing the next number. But at some point, it will just get too hard. You'll have too many pictures. You'll see in a moment. The name of the game is you write down enough pictures that you get a linear relation between them, and then you have something to work with. But if your simplest linear relation is too complicated, you have nothing to work with. You can't get started. So there's and these 14 and 15. They're supposed. Is it really 14 and 15? I was about to say there's some number that's a factorial, but it is not a factorial. Sorry. Anyway, there's some reason why you want some kind of braid-like relation and having the bounds there. Like, if you think of the things you have here are kind of like crossing-like things, and you want a bound here that's good enough to get like a braid-type relation, but not exactly. And so that's why you can't go further than that. Okay? And even for 15, they don't have a full classification. Zhengli needs some kind of genericness condition. It sort of says if the relation between those doesn't have weird 0 coefficients in weird places, then you have a classification. He would state it in a somewhat different way. But,
yeah. You had done 1, 1, 3, 13. Is the answer there are none?
No. Sorry. Whenever so here in these statements, I mean bounded by that. Yeah. So in fact, I think part 1 maybe is a 13. Part 2 is a 14.
Part 1's a 12.
There we go. Anyway, yeah,
And part 3 is 14.
Yeah.
Thank you.
Yeah. Thanks. There's another world of these. Which I don't quite know who to correctly attribute this to, because it's one of these things where people did this work but not exactly in this setup. So I'll mention several people who did stuff along this line. Wenzel and his collaborators, including Kazdan and Tuba. Kaufman in knot theory, though he didn't quite say it this way. Longo and Rarin, not in joint papers, but in separate papers. So the basic setup here is you're looking at something much more not theoretic. So you assume your tensor category is braided. So you know you have a braided crossing. And you don't assume shaded. So here I want some kind of non-degeneracy condition. This is like some weaker version of unitary that makes sense in that algebraic thing. I want some natural inner products to be non-degenerate. What that means is there's no negligibles. If I ever have a diagram that every way I close it off gets 0, I might as well get rid of it. Okay? So that always happens in the unitary setting. In the algebraic setting, you have to kind of put it in by hand. If you want oriented braided, what on earth did I write there? No den? No pen? I don't know. Well, we'll see. There's probably an error where I'm missing something here. Hopefully maybe someone will notice. So hopefully I got this. So now, because things aren't shaded, there's going to be a bunch of zeros because when things are shaded, you could just skip the odd number of boundary points, but now I'm including so this again says this is 0 boundary points, 2 boundary points, and 4 boundary points. Yeah, so I want that. Then you get a classification theorem that says it's basically Homfly. Okay? So what happens is if you look at these 4 boundary point things, you have a crossing this way, you have a crossing this way, and you have this thing. This forces some linear relation between those. Then you try to look at what are all possible linear relations between those, and then which ones actually satisfy the braid relations and stuff, and you'll eventually conclude that there aren't very many options. Okay? And then the second thing is unoriented braided 1, 0, 1, 0, 3. And here you do the same thing, but you get basically Kaufman. So now you have more pictures. The reason this is a 3 instead of a 2 is that in the unoriented world, I can also draw this thing. So I write down those 4. There must be some relation between them. That's enough to get you started. Okay? So this is kind of where this comes from. Any questions about this? So I think this is all I wanted to say about previous work. At some point, I'm going to have to mention Kuperberg's work that is much more closely related, but that'll come up a bit later. Okay, so there are all these different worlds, and you can come up with millions of other worlds where you could try skein theoretic classifications. Great. All right. Now I'm ready to start concentrating on not where our setup fits into the general universe of mathematics, but more explicitly our setting. Oh, so I guess I sort of skipped ahead to this because I needed to have more pictures. So anyway, our setting is non-degenerate, unoriented, and generated by a trivalent vertex, by which I mean a map like this, x tensor x to x, that has the property that when you rotate it, it comes back to itself. So we'll talk a little bit more about that rotation in a minute, but if I start with a trivalent vertex, I could rotate it like this, and I get another map. If I assume that the 3 boundary point space is one-dimensional, it has to give me some multiple of my original map. If I do this 3 times, I definitely get back to my original map. And so it changes by a root of unity, but it could be 1, or it could be a primitive cube root of unity. And so we're first going to do the case where that rotation is 1, so I can actually use pictures exactly like this. And at some point, we'll relax that and say, oh, we need to keep track of a little dot here, so that we know if you move that dot around, you have to pick up a cube root of unity. Okay, so at some point we'll ship that, but when I say by trivalent vertex, I'm including this rotational invariance. That's what we're trying to do. Now, why is this a natural thing to look at? Let me tell you one example that is very useful. So suppose I have subfactor A inside B with B looking like 1 plus x with this x simple. So this is sometimes called a 2 supertransitive subfactor, but it's a very natural setup. I mean, B, that's B breaking up as an AA bimodule. Okay, I look at B as an AA bimodule, so that, and that 1 is A. Sorry, maybe I'm really mixing notation here. B as an AA is A as an AA plus some simple AA bimodule. Okay, that's the setup I want. And the trivalent vertex is the restriction of multiplication up to a scalar. So B here is an algebra. It has a multiplication. I can look at that multiplication in components here, and I can just remember, look at x tensor x, and then project down onto the x part. So I have x tensor x, I multiply them and get something in B, and then I project down to the x part again, and I get some map from x tensor x to x. Okay? So this is an example of a trivalent vertex. Maybe I should say something about why it's rotationally variant. It is. I don't want to say anything about it. Yeah, so this is an example. The reason I put this up to scalar here is that I didn't want to bother with getting normalizations right. So if I make this the actual restriction to multiplication, like, well, then I would have to like pay attention that I got some normalizations right. And if I say it's just that up to rescaling, I don't have to, you know, if you say like that's not multiplication, multiplication would have a square root of the index at that factor. I can just ignore it. Okay, so this is an example, and I want to say what this example looks like scheme theoretically. Okay. Success. I did not push it up too high. That's the trick with this room. So I want to say what this example looks like scheme theoretically, and this is all well-known old stuff coming back to all this Q systems business, but let me just tell you what the relations are. The circle is D. I will never write a 0. If you ever see a circle, it's a strand. If I want the number 0, I will write the word 0. So this does not say 0 equals D. And D here, this is like a statistical dimension or a square root of the index or something. If I look at this...
What about the O in relations? It's a letter. In relations, you have an O.
Oh, yeah. That's true. Yeah. Great. Okay, so the lollipop is a map from x to nothing at all. Nothing at all means the trivial. And so I guess I probably should have said that. X here is some symbol that isn't just A as an AA again. If it's an irreducible subfactor, that's automatic. Otherwise, I can just say it. So this is a map from A to the trivial. There are no such things. So this I want to be 0. This I just call B, and I note that B is not important because if I change my choice of scalar here, it would change the value of that by squaring that scalar. So I could have just made B 1 if I wanted, or I could have made B whatever the right choice was in order to make this actual like multiplication. So if you look at like the definition of a Q system, there's going to be some right number for this, but and then
B times.
What? B times a strand, thank you. And then the important relation that looks like this. Okay. And what is the growth of this category? So the growth for D generic looks like 1, 0, 1, 1. So this is the trivalent vertex. It says there's only one map from X tensor X to X. And then it goes 3. This is like, you might think you had 4 things here, the I, the H, and these 2 things, but there's actually only 3, which is where this relation comes from. And then it goes 6, 15, 36, etc. And it is A 0, 0, 5, 0, 4, 3, if you want to know everything there is to know about it. Okay. So this example is very natural from a subfactor point of view, but it is also comes up in a lot of places that aren't subfactors. So this has 2 other names.
Can I ask?
Yeah.
So it didn't matter what A and B was, you get the same scheme theory, or this was?
Yeah, I mean, this is, yeah. I should say, let me make a point here. So I'm only looking at the maps that you can build out of the trivalent vertex. So if A inside B was some more interesting subfactor, and I wanted to find all of the maps, I would have to look at all of these ones, plus possibly some new extra maps, okay? But when I'm restricting to a specific flavor of scheme theory, so in general, one might do 2 steps. You first classify all the things that you could get just with the trivalent vertex, and then once you've done that, you go back and say, can I add more higher things? And then you would get into something like a classification of subfactors, okay? So you get different tensor categories for more interesting, depending upon what A and B is, but you don't see that just from the trivalent vertices. So basically this is saying that the trivalent vertices are only seeing the temporally lead part of the planar algebra.
Could you also be less interesting?
What do you mean? Like,
depending on A and B, could there be additional relations?
Oh, yeah, if the index was small, you would get some quotient. So that's why I say D generic. You would get some relations, and those relations are like, you write down, you know, like your relation saying, you have to figure out how to write Jones-Wenzel's in terms of the even part, like, all of this is like even parts of temporally lead. And so then you have to say, like, can I write down the Jones-Wenzel's and then contract all the shaded things, and then, you know, put JW2s everywhere and contract down, and it gets a little tricky. But yeah, if D is some sort of weird small number, this growth will be smaller, and you'll have to take some quotient to make it be non-degenerate. Yeah?
This is not related to Fibonacci category, right?
Fibonacci category is this, when you take D, if you take D to be the golden ratio, then this will be degenerate.
And the sequence of numbers change.
And it will go down to 1, 0, 1, 1, 2. That's right.
And that's Fibonacci.
Yeah. And you'll be able to individually simplify either the I or the H, but it will still be true that I minus H satisfies that relation. That's a great question. Yeah, because I need to mention the Fibonacci category later, and I didn't put it in anywhere. Any other questions? So when I say this has 2, what do you call, like, names a criminal goes by? Alias, is that? I thought there was anyway. This is 2 aliases. The first thing is that it's SO3Q. So this is what I'm saying. It's sort of like the even part of temporally lead. It's the quantum version of representations of SO3. There's a small caveat to that, which is the D here is a quantum 3, and the thing that it's an even part of has like a quantum 2. And if that quantum 2 vanishes, but the quantum 3 doesn't vanish, then non-degeneracy gets weird. So there's actually one bad value of Q where SO3Q doesn't really make sense, but the scheme theory makes sense. And that corresponds to something that Lie superalgebraists call OSP. Is it 1/2 or 2/1? Which do you put first? Yeah, 1/2. Great. Okay. So that's one name it has, is that it's a quantum SO3, except one bad point, which has some other name. And the other guys is that it's sort of the chromatic, or maybe better to say the flow polynomial. So if you make the right change of variables, the answer to this tells you the chromatic polynomial of the number of ways to draw the faces of your graph. So you have your planar graph, you count the number of ways to color the faces with n colors. That will be given by evaluating your graph using these skein relations for d some particular function of n. D isn't exactly n, it's a little bit off, okay? Yeah?
Is it possible to say for which parameters it is semi-simple?
Yeah, I mean, the values where you have to take a further quotient are the ones where d is quantum 3 corresponds to a root of unity.
It's not just relation between t and b, it's just d being.
Yeah. Yeah, b doesn't mean anything.
Oh, B
I
doesn't
could make
mean-
b
oh,
to
yeah,
be
it's-
1
it's-
if
it's
I wanted
scalable,
it to.
yeah,
Yeah, yeah,
okay,
b
yeah,
has no
cool.
meaning.
Yeah,
It's just to make it so that I don't lie to you. Yep, any other questions? Okay, so, right, so I want to actually, I'm going to prove a lemma. Rather than proving any of our hard theorems, I'm just going to prove an easy theorem in the same direction to just show you how this stuff works. That's actually about this, but it's actually pretty useful for subfactors. So the theorem is, or a lemma, and this lemma is in the paper with Scott and Emily, but there's an earlier version of it in a paper with Pinhas. So if it starts 1, 0, 1, 1, 3, then you have to be SO3Q. I guess I should say SO3Q or OSP 1, 2. You have to satisfy a relation of that form. Okay? And I'm not going to go through that. At some points here, I will say, then there's an annoying corner case where you do something, and I'm not going to go through every detail, but I want to give you the idea of it. So what happens? Well, you know, because there's a 3 here, that if you write down those 4 diagrams, there's some relation between them. So you have that relation. If that relation holds, you can rotate it 90 degrees and you'll get another relation. Okay? So either this gives you 2 relations and you get a huge drop and you can just simplify I and you can show that has to be this Fibonacci golden category, or you get back to a multiple of the same relation that you started with. If you rotate twice, all of these pictures come back to each other. So whatever that number is has to be plus or minus 1. Okay? So this says you have 2 possibilities for what this relation could look like. It could look like this plus this equals some multiple of this plus this. Or it could look like this minus this equals some multiple of this minus this. Okay? In this case, we're getting very close to what we want, but it's quite easy to get exactly what we want. So if this relation holds, the same relation has to hold if you cap off on the right. So I just connect these 2 things, I connect these 2, I connect these 2, I connect these 2. Then what happens? This one gets me b times the strand. This one goes away because there's a lollipop. I should have strands everywhere, but I'm not going to draw them because the 2 boundary point space is 1-dimensional. Anyway, 2 multiples of the strand are just equal if those numbers are equal. So here I get b minus 0. Here I get z times, here I pick up a d from a circle, and here I don't, d minus 1. So this tells me that z is b over d minus 1, which is hopefully the number that I wrote up there. Yep, great, okay? Now on this side, you can try to do similar things. So the same argument will tell you that z is b over d plus 1 by the same argument I just did there, just cap off on the right. Okay? If I put a trivalent vertex on the right, here I'll get a triangle, here I'll get a trivalent vertex pulling out a b, here it'll go away. You know, you can figure out what happens here. You get that the value of the triangle, so I'm going to say because there's only one 3 boundary point, the 3 boundary point space is 1-dimensional, value of the triangle is some multiple of the trivalent vertex. I'm going to call that multiple t. So here I get a t, here I get a b, here I get z, which is here I get a z, I get a z here and a 0 here. So I just get a z, and remember z was b over d plus 1, and I can solve that and get that t is minus bd over d plus 1, right? So you can solve for what t is. And now you get stuck for a long time. And you think, what else can you do? And there's a fun trick, which is you put everything in a square. So if that holds, it also has to hold. So everything makes sense here. They're all trivalent vertices. This plus this has to equal z times this plus this. Okay? This relation was useless on the minus side because everything would just cancel, right? You'd have this minus this. But here it collides, so you get some actual relation. And you can try to simplify this. This one, so I'm going to divide by 2 and just say this means this has to be the same as this, and just tell you what that formula is. So here I get t squared bd. So I get a t here. If I remove that triangle. Now I get a graph that just looks like a theta. I remove one of the bigons, I just get a circle, and then the circle is d. So I get t squared bd should be equal to z, which was b over d plus 1, times, here I remove a bigon, and then I have a circle, so I get b squared d. And if you just simplify this, using our formula for t there, you'll get that d squared is d plus 1, which means that d has to be the golden ratio. And at the golden ratio, in fact, both of these relations are degenerate. Okay? So you have to think a little bit about that. So once you have a relation of this form, all arbitrarily giant pictures, once you have a relation of this form, you can show that any 4 boundary point diagram is one of these 4. And then you can say, oh, to show that it's non-degenerate, I just need to take to see that something is degenerate, I just take inner products with those 4 things. And if those 4 things vanish, then I have something degenerate. And you use that to show that not only did you have this relation, but this relation is also degenerate, and you're down to just the golden category, the Fibonacci category. Okay? So that's why this plus side doesn't work. And this is a general feeling of how these kind of scheme theory arguments work. You get some dimension bound. The dimension bound says you have some relation between some things, and then you start doing some calculations to say, oh, what could this relation look like? You hope you eventually get enough to know all the things, but at some point during that argument, you need to make some argument that says, oh, to check degeneracy, I might need to know that the diagrams that I know about span, and that makes life a little confusing in certain circumstances. But this is roughly how all the arguments go. Okay? Any questions about this? This is the style. All right. So now having given you the idea in an easy example, I just want to tell you what our results are. So first I have to tell you what Kuperberg's result was. So all of this was inspired by an old paper of Kuperberg's, where what he proves is that if the dimensions are exactly 1, 0, 1, 4, 10, so I increase the 3 to a 4, and now to get anywhere I need some bound on the next one. This is often how it works. Plus a little bit more. So what do I mean by plus epsilon? So he says not only are the dimensions bounded by those, but the obvious diagrams form a basis. Okay, so the obvious diagrams here means the diagrams with no faces. Okay, so here this is saying you look at the 4 diagrams that you can look that have that are the I, the H, and those 2 things, and the square needs to simplify into a sum of those 4. Okay, so if you have this, then your G2Q, the quantum group for the exceptional Lie group G2. Okay, so this is what we wanted to understand. So our goals were kind of threefold. Include corner cases. what if those 10 diagrams aren't linearly independent? Well, if they're not linearly independent, you get some relation between them. That relation is already enough to start simplifying things, so you should still be able to do the calculation. It just might be more annoying. Okay, so we wanted to include the corner cases. We wanted to increase 10 to 11. And now the price of that is going to be a bound on the next thing. And we also wanted to look at what happens when you allow these twisted trivalent vertices where you have to keep track of the direction so that when you rotate it, you pick up a cube root of unity. Okay? So that was our goal. So now I will tell you what we succeeded in those goals. So I'll tell you a little bit about the techniques after this, but I first just want to tell you what we found. So there's going to be two cases, the untwisted and the twisted one. So the untwisted one is where you don't need those extra dots and cube roots of unity. So if it starts 1, 0, 1, 1, 2, that's the golden category. If it starts 1, 0, 1, 1, 3, that's this SO3Q thing. So that's the theorem I already told you how the proof went. Now if it goes to 4, if I put an 8 here, there's one new example, which is an interesting free product construction. You take the golden category, that is temporally Lieb at, you take temporally Lieb at D as the golden ratio. You take its free product with a generic temporally Lieb, and then inside of that, you pick your favorite object to be the one that looks like ABA. So it's, sorry, no, this is not temporally, this is golden. What I have written here is wrong, right? Well, anyway. That's the golden, or the Fibonacci category, or whatever you like to call this. So what happens here is you look at pictures that look like A, B, A. So the B's live in the Fibonacci category. The A's live in a generic temporally Lieb. And this is some kind of free product picture. Okay? So this was kind of it's not new in the sense it still lives on that list because it comes from quantum groups via free product construction. But it wasn't an example we sort of knew about before running into. Maybe we should have, but it wasn't on our list until we did this. Then you get G2. Usually G2 has a 10 here. In some cases, it has a 9. I feel like I didn't tell you something. Oh, yeah, I didn't tell you something. I'll do it after this. OK, so I wanted to tell you something about why these 4s and 10s were important. So I'll do that in a moment, why Kuperberg's argument works. So if you go up to 10, you get G2. If you're at the right small root of unity, that 10 actually decreases, but that's not important. And then we said, what if we increase that 10 to 11? And then we're able to go all the way up to 40. There's only one new example, and it's what Pinhas and I called H3. It's something Morita equivalent to Hagerup, but it's not itself Hagerup. Okay? Now, it shouldn't be Hagerup because what are these things? These are bimodules that look like they might have a tensor product, or look like they might give you an algebra. They're bimodules that look like they might have come from a factor, an overfactor, but they don't. They're like, here we're kind of classifying the ways a bimodule can sort of fail to give you a subfactor. They're interesting bimodules, so these ones come from subfactors, and these ones are things that might come from a subfactor, but they don't. These are the ways that things fail to come from a subfactor. So this theorem I told you is actually pretty useful because it's a way to guarantee you had a subfactor. Like you're trying to produce some bigger factor, and you can just say, oh, if that dimension is 3, you're done. Okay? All right. So yeah, so this of course fits into Izumi's world. So we didn't find anything new, which is a little disappointing, but it maybe suggests that we just started looking in somewhere totally different. The first weird thing we found was an Izumi quadratic category. Maybe that means there's less weird stuff out there than we thought. Okay? Now in the twisted case, you can ask the same question. So if you put 1, 0, 1, 1, 3, there's an interesting example, which is like it's like a twisted version of the representation theory of S3. Okay? And it can be constructed in some standard group theoretic way out of S3. Okay? Using some cohomology and a subgroup, and but it mostly kind of looks like S3. It comes in two flavors depending on which element of the cohomology you've done, corresponding to the two different choices of root of unity here. So you get something there. If you try proving Kuperberg's thing, you find there's nothing else new. Okay? So for Kuperberg's setting, nothing else new. Here we get a twisted version of Hagerup. This is a version of the even part of Hagerup where you have a non-trivial associator on the invertibles. There's no subfactor there, but there's a perfectly good collection of bimodules. There's nothing over 39. At 39, there's exactly one candidate, which we don't know whether it exists or not. So we can give a complete description of it. We can give generators and relations, and we know that those relations are enough to know everything about it, but we don't know whether it exists or not. So that's why I put 2 question marks here. We don't know if it's there. There would be exactly 2 of them, one for each root of unity. Now the sad news for here is that D is -1, so it definitely has nothing to do with operator algebras. It's not braided. The dimensions of objects aren't real, which means it can't be fusion. It's weird, but it might be there. We can't kill it. So anyway, maybe we succeeded. Maybe there is one weird thing there. Unfortunately, it's not very operator algebraic, but it's possibly there. Okay, so yeah.
What about just representations of S3?
Representations of S3 is secretly here.
Oh, it's secret. It's untwisted, right? Oh,
Yeah.
it's untwisted, right? Yeah. Of course.
Yeah, the representations of S3 is the even part of the A5 guy, and so it's secretly here at the right root of unity. Yep. Any other questions? Yeah.
Is this Q omega, is it supposed to be finite or infinite? Or?
It has to be infinite because it's spherical and the dimensions aren't real. So if something is spherical and has and finite, the dimensions have to be real.
What do the dimensions look like?
They're 6 roots of unity. Yeah. We have a guess for the fusion graph, but that's it. So I just want to end by saying the techniques that we use. So for Kuperberg, the key technique is that you can simplify pentagons and smaller faces. Okay. So the fact that you had a 4 for the 4 boundary point diagrams essentially tells you can simplify a square into those 4, IH, identity, and cup cap. Okay? And then that 10 tells you can simplify a pentagon. So you can simplify pentagons, squares, triangles, and bigons. And then there's a very easy argument that Euler characteristic implies that any trivalent planar graph has a small face, a face that's a pentagon or smaller, and now you have enough relations to understand everything that's going on, and that's what makes Kuperberg's argument work. Okay, so we want to do something similar. So the techniques we use to adapt his stuff, so we needed 3 things. One is computer scheme theory. So we knew we were going to have to look at much bigger things, so Scott has this amazing scheme theory machine that will, allow you to do scheme theoretic calculations that you could, you would try to do them by hand for small things, but for big things, you don't want to keep doing that. In order to make things more more amenable to computers, we don't exactly prove arguments in the style of that proof that I gave you. What we instead would do is write down 5 diagrams, the I, the H, those 4 diagrams plus the square. We would compute all their inner products. We would get some matrix. We would compute the determinant of that matrix. We would say it has to drop, and we would use computers to, computer algebraic geometry packages to try to do that. And the third idea is something called discharging, which was the technique developed to prove the four-color theorem. Four-color theorem involves a very hard discharging argument. All we use is a very easy discharging argument. If you go to the Wikipedia page for discharging, it will prove one lemma for you. And it does it in the article, and it says the lemma is any closed trivalent graph has a square or smaller face, or two adjacent pentagons, or a pentagon next to a hexagon. And that's the theorem we prove that allows us to turn, we use that theorem to allow us to turn that 10 into an 11. Okay? And that's all I wanted to say. Thanks.
Any questions or comments?
So you mentioned that you found H3 there. So in many of these algebra-presuming categories, it's like a duality where either there's an algebra structure for 1 plus x, or the other one doesn't have an algebra for 1 plus x, but it does have an algebra for 1 plus all the non-reals besides x. Is there any way in this game theory to see those other algebras? Like 1 plus gx plus g squared x?
Yeah, usually it's bad. I mean, you can, you know, like, I mean, you know that, you know, for, I mean, those bigger objects appear in the game theory as having many boundary diagrams, and then trying to see the algebras is hard. This is like this extended Hagraf calculation where you have to write down, you know, 55 million numbers, right? Like, the calculations get big fast. They won't get as big here, but it would still looks a little scary to me. Game theory, right? Planar algebras are a technique where you have a favorite object. And once you start changing your favorite object, life gets hard, and it's not necessarily the right technique. So these kind of scheme theoretic planar algebra arguments are really best when you don't want to change favorite object. Yeah.
What kind of relation is this Q omega? You said you guys could write down
Yep, it's there. Yeah.
do something hexagons or something?
Yeah, so there's a relation. I mean, what we show is there, if you look at the 6 boundary point diagrams, so you have a hexagon and you have a bunch of pentagons with a fork sticking off of it, and you get 2 relations among those, and then we show that having 2 relations among those is enough to reduce 2 adjacent pentagons and a pentagon next to a hexagon. And so what you can look up in there is those 2 relations explicitly with pictures. Yeah, we like to call it Angry Bird because one of the pictures, or I like to call it, I don't know, one of the pictures there really looks like a like Angry Bird video game, but yeah. Yeah.
Is it possible to define the boundary between these kind of finite ranges and the what you were sort of alluding to as being wild? Like it looks like there's a sequence 1, 0, 1, 1, 4, maybe 11.
Yeah, so you could, if you wanted to go back and prove a much harder discharging theorem, you could try to increase these. Like, I bet if you put in as much work as was put in to prove the 4-color theorem, you could make these numbers much bigger. But it depends on how hard of discharging results you want to prove, and it's going to quickly like become things where you're like using the computer for the proof as well as the calculation. But I don't know what those numbers are. I mean, yeah, here like.
Is it even clear why it would be a finite list? Maybe this is naive. If you fix the first few, I mean it seems like some parameters there's a finite list, and some parameters you seem to imply there's an infinite list of possible.
No, and in fact, we probably believe the opposite. When the numbers get big, there should be no examples, but the proofs get impossible.
Oh, I see.
Yeah.
Do you know anything about the long-term growth?
Oh, for each of these examples, we do, but.
Is it exponential or polynomial?
Right. It sort of depends on whether your thing is finite or not. Like if you're, no, sorry. It should, like, usually often it's exponential.
Oh, sorry. Yeah.
But for Q omega, it won't be. Like our guess for the principal graph of Q omega is kind of fractal and keeps splitting, and I don't necessarily expect exponential growth for Q omega. For all the other ones, I'd expect exponential growth. No.
Exponential growth. You have a 5 factor, so you.
Yeah. I'm worried about things like how BMW at bad parameters has factorial growth instead of exponential growth. That's the kind of thing. Anyway, I'll think about it. But
These dimensions of high relative commutants?
yeah, but
Then they actually grow exponentially with the index being defining the face of the exponential, right?
right. All of these ones are all of these ones are fine. Some of the ones I drew earlier in the thing are not, and Q omega is maybe not. Yeah, they don't. I mean, at bad values of the parameters, they might not come from subfactors. That's sort of. But yeah, of these examples, they're all fine except maybe Q omega. I'm scared about. It definitely doesn't grow bounded by exponentials in -1. So.
Any more questions? If not, then let's thank Noah again.